So today we are looking at a paper called Trust Region On-Policy Distillation, or TrOPD for short. It's by Xingerun Jing and a team from Samsung Research, the University of Oxford, and Peking University.
Yeah, it is a really fascinating one.
It really is. And to just jump straight into the core insight here, right now, if you try post-training small reasoning models using on-policy distillation, it usually just, well, it crashes.
Oh, completely.
Right. You get these severe distribution mismatches between the teacher and the student models. And when you try to save memory by using these K1 estimators, those mismatches basically cause your policy gradients to literally explode to negative infinity.
Which is obviously a catastrophic failure.
Exactly. But TrOPD solves this by dynamically dividing the students' generated tokens into two buckets. You get a trust region that gets optimized safely via reverse KL divergence, and an outliers bucket that gets salvaged using a top K forward KL estimator.
And they also throw in off-policy teacher prefixes, too.
Yeah, to guide early exploration. And the result of all this is that it consistently beats state-of-the-art baselines like Leopold across math, code, and STEM benchmarks.
Which is exactly what the industry has been desperately looking for.
It is. So welcome to AI Paper Slop. This is our YouTube series where we do a deep dive into the latest and greatest AI and tech papers.
Glad to be here for this one.
Yeah. For those of you listening, whether you are an ML engineer tuning models or a researcher tracking the bleeding edge, you know why this matters. The whole AI community is just obsessed with large reasoning models right now.
Definitely. But deploying them at scale, it's a total logistical nightmare.
It's way too expensive.
Yeah.
So to get these advanced reasoning capabilities onto efficient single-digit billion parameter models, we have to master distillation. And TrOPD is just this massive leap forward in making that process actually stable.
Right, because right now, that transition from large to small models is brutal. You're basically trying to transfer the internal chain of thought from a massive teacher to a smaller student.
Yeah.
But there are these huge mathematical roadblocks. Like, think about conventional off-policy distillation. It's essentially like trying to learn how to navigate a complex maze by only watching a drone fly over it perfectly.
Oh, that's a good analogy.
Right, you memorize the perfect path. But the moment the student is on the ground and takes one slight wrong turn, which they will, they have no idea how to recover.
Because they've never practiced making a mistake.
Exactly. This is called exposure bias.
Yeah.
And for long chain of thought reasoning tasks, which can, be thousands of tokens long, exposure bias is fatal. The moment the context gets weird, the whole output collapses.
So that naturally forces the community to pivot to on-policy distillation, or OPD.
Yes.
So if off-policy is watching the drone, on-policy is forcing the student to actually run the maze themselves.
And make your own wrong turns.
Right. They sample from their own policy, generate these student-generated trajectories or SOGs, and make mistakes. Then the teacher comes in and evaluates those specific flawed paths to teach recovery.
But doing that introduces a massive hardware problem. The dreaded memory wall.
Right, because if you want to compute the full vocabulary reverse KL divergence to update the student model, it's just mathematically impossible on standard hardware.
Yeah, the math is inescapable there. To compute the full divergence, the memory complexity scales as O of n times k.
So n is sequence length and k is the vocabulary size, right?
You got it. So imagine a modern reasoning model writing a complicated mathematical proof. You might have a sequence length of, say, 8,000 tokens.
That's just pretty standard.
Yeah, and then multiply that by a typical vocabulary size of 128,000 tokens. You are essentially asking the GPU to hold a billion-element probability matrix in VRAM just to calculate the divergence for a single sequence.
Oh, wow. Yeah, that would just instantly blow out the memory of almost any GPU cluster.
Totally. It just doesn't work.
Wait, hang on. If the hardware limitation is really that severe, how is anyone actually doing on-policy distillation right now? I mean, we know people are training these models.
Right. Well, they use estimators. Specifically, they rely on the K1 estimator.
Okay, how does that work?
Instead of computing divergence over the whole 100,000 plus vocabulary, the K1 estimator just estimates the reverse KL using only the single token that was actually sampled by the student at that step.
Oh, I see. So that drastically shrinks the memory footprint down to just O of n.
Exactly. It makes it computationally feasible.
But wait, let me push back on that for a second. If we are using the student's own policy and the student is weak because it's learning, it's going to sample some terrible tokens.
Oh, definitely.
Like, it might hallucinate a totally nonsensical variable in a math equation. So if we are estimating the gradient based only on that one garbage token, the teacher model is going to evaluate it and assign it a probability of practically 0, right?
Yep.
So what does the K1 estimator do then? What happens to the math when the teacher's probability hits 0?
And that right there is the exact cause of the collapse.
Really?
Yeah. The objective function relies on the log ratio of the teacher's probability to the student's probability. So when the student is super confident about a hallucination, but the teacher assigns it a probability near 0, taking the log of that drives the policy gradient toward negative infinity.
Oh, geez.
Yeah, so your gradient just plunges off a mathematical cliff. Nubble or J. Dillers goes to negative infinity.
It's kind of like an audio feedback loop at a live concert. You know, when a mic gets too close to a monitor speaker.
Exactly like that.
Instead of just logging a bad note and moving on, the system recursively amplifies the error until the amplifier completely blows out. So the K1 estimator does that to the optimizer. You get a massive outlier, and the neural net weights are updated with an error signal of negative infinity.
And your entire training run is ruined.
So what are researchers doing right now to fix this? Because we clearly need K1 for the memory savings.
Right, so the community has come up with a few band-aids to try and stop the gradients from exploding.
Okay, so let's evaluate those failed fixes, because I think understanding why they fail is key to why TrOPD actually works. The first one I see a lot is entropy filtering, like in GRPO.
Yes, very good.
The idea is you just filter out the danger entirely. You only train on the top 20% of tokens with the highest entropy. Basically, the tokens where the student was the most confused.
It sounds totally logical on paper, right? Focus the learning on where the student is uncertain.
Right.
But the authors of the TrOPD paper actually ran extensive benchmarks on this. They use a Skywork OR1 Math 7b model as the teacher to teach a DeepSeek Qwen 2.5 1.5b student model.
And what did they find?
They found that entropy filtering actually degrades performance compared to doing nothing at all.
Wait, really? It degrades it. But if you filter out the explosive gradients, shouldn't it at least keep the training stable?
It does keep it stable, but you end up starving the optimizer. Think about a long chain of thought. The vast majority of those tokens are just ordinary low-entropy tokens. Formatting, standard notation, simple logical connectors.
Right, the easy stuff.
Yeah. The student is confident, and the teacher perfectly agrees, which provides great foundational supervision. When you throw away 80% of your trajectory just because it wasn't high entropy, you throw away all that foundational learning signal.
So the student basically forgets the basics because it's only studying the weird edge cases.
Exactly.
Okay, so entropy filtering starves the model. What about reward clipping? I know Leopold uses that, and it's a pretty respected baseline.
Yeah, Leopold uses reward clipping, which is essentially putting a hard ceiling and a hard floor on the reward.
Yeah.
You set a hyperparameter, and if the gradient tries to go to negative infinity, the clipping function just caps it.
So you physically stop the audio feedback loop from blowing out the amp.
Right. And it does help slightly compared to the raw baseline. But it introduces a really finicky hyperparameter that you have to tune constantly. And more importantly, it's just a blunt instrument.
Because it treats all large gradients as errors.
Exactly. Sometimes a massive divergence between the student and the teacher contains a really profound lesson about reasoning. By just chopping off the top and bottom, you suppress the crashes, sure, but you also throw away the most informative outliers.
Wow. Okay, so we're stuck in this massive routing problem. Full reverse KL is too expensive. K1 explodes. Entropy filtering starves the model, and clipping throws out the best lessons.
Right. So how do we safely learn from the student's wild generation?
And this is where TrOPD brings in the trust region, right? Let's get into part 1 of their solution.
Yes. The trust region is the core mechanic. Instead of these arbitrary thresholds or hard clips, TrOPD uses something called the decoding agreement ratio.
Decoding agreement ratio.
Yes, okay, for every token the student generates, the system calculates the ratio of the teacher's probability for that token to the student's probability.
So the probability of a token entering the trust region is mathematically the minimum of that ratio, or the number 1. So if the teacher thinks the token is more likely, or exactly as likely as the student does, the ratio is 1 or higher. The minimum function caps it at 1, meaning it's a 100% guarantee that the token enters the trust region.
Yes, and as long as it's in the trust region, it gets optimized normally using the K1 estimator. It's totally safe because that ratio guarantees the teacher's probability isn't near 0, so the log ratio can't explode.
That's incredible. It's like Well, think of speculative decoding. It's like having a senior engineer review a junior engineer's code line by line.
That's a great way to put it.
Even if the junior's code isn't the exact style the senior would have written, as long as the senior engineer thinks, yeah, this is plausible, it compiles, it goes into the trust region and gets normal optimization.
Exactly.
But wait, the student is a junior engineer who will absolutely write total garbage sometimes.
Oh, frequently.
Right. So what happens to the tokens where the student writes nonsense? Those can't go in the trust region.
Right, they don't. Those tokens get routed to the second bucket, the outliers. And here is where TrOPD completely abandons the K1 estimator. Instead of masking them out or clipping them, it uses a top K, forward KL estimator.
Forward KL. Hang on. If the student has gone totally off the rails, the context is already ruined, isn't it?
Yes, the context state is severely degraded.
So why use forward KL to try and force the student to imitate the teacher's top K tokens in that specific broken spot? Isn't that just going to confuse the model more?
That is the brilliance of the paper. This auxiliary FKL objective actually have a built-in self-suppression mechanism.
Really? How so?
If you look at the math for forward KL, the divergence is calculated as an expectation of the student's generated policy.
Okay, so it's weighted by what the student thinks.
Exactly. So if the trajectory is so far gone that there is absolutely zero overlap between what the student thinks comes next and the teacher's actual top K tokens, the student's probability for those teacher tokens is zero.
Oh, wow. So mathematically, that specific term in the gradient expectation gets multiplied by 0.
Yes. The objective naturally suppresses itself. It doesn't break the gradients, and it dynamically saves useful knowledge without forcing impossible imitation.
That is so elegant. If there's a tiny sliver of agreement, like maybe the context is weird, but the student still outputs a correct formatting token,
Right.
it captures that.
Exactly.
But if it's unsalvageable garbage, it just zeroes out and safely ignores it.
It perfectly dynamically routes the optimization.
Okay, so that's gradient routing solved. But let's move to part 2 of the solution, because even with perfect routing, there's a glaring mechanical issue here.
The cold start problem.
Yeah. If you start training a weak student model, its initial SOGs are going to be terrible, just pure noise.
Which means almost every token becomes an outlier, and the trust region stays empty.
Right, and since the FKL objective suppresses itself when there's no overlap, the optimizer is just going to starve at step 0. So how do they get it moving?
This is where they introduce the final piece of the puzzle, off-policy guidance.
The training wheels.
Exactly. To jumpstart the learning, they split the distillation trajectory into 2 parts. The first part of the sequence, let's call it X, up to index L, is actually generated by the strong teacher model, off policy.
So they just feed the student a really good prompt prefix.
Yes. The student ingests this high-quality prefix, and then at index L, the student takes over and generates the rest of the sequence on policy.
Okay, but how do you transition away from that? Because eventually you want it fully on policy.
They use a cosine annealing schedule. So at step 0 of training, the off-policy teacher prefix is very long. The student gets a ton of good context to evaluate, which immediately populates the trust region with high-quality gradients.
Makes sense.
But as training progresses, the length of that teacher prefix is gradually annealed down to 0.
Like training wheels on a bike. They automatically retract as you pedal faster until you're riding completely on policy by the end of the run.
It perfectly bridges the gap.
Okay, so theoretically, this trifecta trust regions, outlier salvage, and off-policy guidance is flawless. But let's look at the hard data. Does it actually work on the benchmarks?
It really does. They started with single-domain math evaluations using a DeepSeek distilled Quinn 1.5b model.
Okay, and the numbers?
On the AME and AMC mathematical reasoning benchmarks, TrOPD boosted performance by an average of plus 3.06 points over standard on-policy distillation.
Wow.
Yeah, and it beat RIPOLD by nearly 2 full points.
A 2-point margin for a 1.5 billion parameter model on AIM is huge. But math is pretty structured. What about messier domains?
That's where it gets even more impressive. They tested multi-domain domination using a Quinn 3 Nematron 4b, teaching a Quinn 3 SFT 1.7b.
Right, and they hit math, STEM using GPQA, code with live code bench, and instruction following with IF bench.
Exactly. Stabilizing gradients across all those wild probability distributions is incredibly hard, but TrOPD still achieved an average gain of plus 3.44 points across all of them.
That is wild. And there was this one fascinating detail from the ablation studies I wanted to bring up. They tested TrOPD alongside a concurrent paper called AOPD, which stands for Asymmetric On-Policy Distillation.
Oh, yes. That was super interesting.
Because usually when you stack 2 SOTA distillation methods, they step on each other's toes and degrade performance, but they found these 2 are completely orthogonal.
Yes. Instead of competing, Combining TrOPD with AOPD bumped the average score up even higher, going from 40.63 to 41.67.
Which just proves that TrOPD's trust region routing is operating at such a foundational level that you can just stack other token-level strategies right on top of it.
It cleans up the optimization pathway that well.
Amazing. So to quickly recap for everyone listening, TrOPD uses trust regions to keep K1 gradients stable, outlier estimation to salvage bad trajectories without forcing impossible imitation, and off-policy guidance to bypass the cold start problem.
And stepping back, I think this leaves us with a really provocative thought about the future of AI. Yeah, if TrOPD proves that small models can perfectly mimic the reasoning traces of massive LRMs just by mathematically filtering out the unstable gradients, does this mean the intelligence gap between large and small models is purely an optimization routing problem?
Wow, that's a wild thought.
Right. In the future, will training small reasoning models look less like traditional machine learning and more like dynamic traffic control, just constantly routing between safe exploration and imitation?
If that's true, it totally upends how we view edge computing. We might not even need to deploy giant models if micromodels can just dynamically, perfectly route their own training data.
It completely changes the landscape.
Well, that is definitely something to chew on. Thank you to everyone tuning into this deep dive for AI paper slop. If you want to dig into the exact gradient equations yourself, definitely check out the project's GitHub page. Keep reading, keep building, and we will catch you next time.